Alrighty, welcome folks. We are going to jump into module number 5 for computer graphics. So let's go ahead and jump into it. And today is a particularly exciting day because we are going to be learning about modern OpenGL. So for those who are enjoying the rasterizer or learning about the rasterizer, that could be a potential final project to carry that forward, but now it's time to get into the good stuff, the stuff that you're likely to use if you're programming professionally in OpenGL. So we're going to dive into it, into Module 5, and talk about two of the big ideas with using the OpenGL Graphics API. And this will be true of other APIs as well. So let's just go ahead and dive into it here. So diving into our slides, let's enter presentation mode. And just a little fun pre-class warm-up. This is me in 2018 at the SIGGRAPH conference inside a little bubble here. And this is one of the famous graphics images. Here is the original paper here. And it was describing various illumination models that could be used. So you can see the floor here, that's checker, that's sort of a staple in computer graphics. The light coming through the window, and then some different shapes. So people have adapted that scene. This is what's called a ray traced version of it, with a giant translucent shape and a reflective sphere and so on. But anyway, the takeaway from here is this is from the conference called SIGGRAPH. It's where you're going to find the latest and greatest information on computer graphics. It really is a great source of information, great if you can attend or perhaps as a student volunteer where you can usually get free access to the conference, and it would be a great place to network for folks who are thinking about careers in graphics. So SIGGRAPH's definitely the name to know. A lot of other fields, whether you go into, machine learning, software engineering, programming languages, whatever it is, they have many, many top conferences, but SIGGRAPH is sort of unique in that all of the graphics people sort of gather at this one conference, and it really is the leading conference. There's some other big ones too, but this really is the Super Bowl or championship, if you want to think about it that way, of conferences in computer graphics, both industry and academic. So it made it really fun. I remember this particular year they were doing a bunch of Star Wars talks and had people from film industry there, as well as the superstars in academia. So anyway, just a little bit on that for folks. We are recording, and we are talking about logistics now. So the logistics are I'm going to be releasing Lab 5, so you'll get to be doing a little bit of OpenGL. There's 2 parts to the lab where you'll be getting started. And then just another note to make sure that you're still completing the in-class activities, just to make sure that we keep everybody up to speed here. Assignment 3 has also been released. It's already been pushed to your repository. I'm gonna probably be pushing assignment 4 as well relatively soon. Again, I know there was a request that I said I'd honor to just kind of push out more assignments faster so you'd have more time in case you got done early. And you should be seeing some grades starting to roll in on Canvas, whether the in-class activities or the lab. So just keep an eye out on that. So last time we wrapped up our discussion on software rasterization, but we were also looking at the transformation in viewing pipeline, talking a little bit more about various transformations that take place and so on. So that was last time, and we're going to move on from that, as I mentioned, and see the end of our software rasterizer, the great looking renderer. Too bad. But by the end of the last lab, you should have hopefully been seeing something, or rather the assignment, something like this, the spinning cube. You've still got a little bit of time to work on it as well. But this framework, or the sort of core that I've provided, really can get you, to building a pretty decent graphic scene where you've got, the vertices. You could fill this in different colors. And you could probably add an abstraction layer for what our assignment 3 is going to be, actually loading 3D models that you create, okay? So anyway, we got pretty far here. We still have some challenges and things that we would want to take care of in our graphics pipeline. But this could be another candidate for a final project if you wanted to push this a little bit further. Okay, so sort of doing texturing or shading this in or whatever. Adding a more convenient abstraction for rotating, translating, and scaling, for example. would also be some other ideas. Okay, so just talking about the fixed function pipeline again. Older graphics APIs, old versions of OpenGL use this fixed function pipeline, what we were essentially implementing here. If we continued with our software rasterizer, we would, keep implementing each of these individual stages and build up some of these functionalities, right? So again, we started with in our pipeline generating some 2D or 3D data. This could be color information. We'll talk about textures, eventually normal information, and so on. And then we assemble this, our primitive, into triangles. Okay, so I don't know if folks look closely, so I will show you here in our repository that we were actually doing some assembly of these primitives here. So let me go ahead and hop in the source in the mesh here. You could see we were building up our vertices, and then we were actually specifying which of these vertices. So the first one, which would be here, index 1, index 0, and index 3, that's what made up our first triangle here. So we had something called an index buffer here. And we're going to talk about that again, but that actually was part of our other framework if you want to use that as a reference. But that's what we're doing when we're assembling our primitives. And then we got on to do some transformation, not so much lighting here, we just lit everything sort of evenly, but we were able to rotate, we could scale or transform our individual vertices and then rasterize our object to eventually fill it in, which is pretty neat. And then during the next stage, again, we might handle some other things like clipping and so on. And then eventually we start filling in our pixels, okay? Figuring out what these fragments are. Then we might have other stages such as texturing, so that would be applying some image on top of our triangle. We might do other different tests like with a depth buffer, if we have translucent textures, things that we can see through, and we need to use that Z buffer, for example. And finally, as we keep going through these stages, maybe we're doing some blending of two different colors and some final sort of dithering, which is a technique to sort of make images blend, I guess, a little bit better and sort of blur. And then finally, we get to the end, which is our frame buffer, which is where we actually draw our image to. Okay? So that's just, sort of a review of the fixed function pipeline. The sort of old school stuff, and we were implementing, each of those stages there in our great looking render. So, there's plenty more steps to take to finish our pipeline. We could continue emulating what has been done before, sort of following this pipeline of plotting vertices, building triangles, transforming them, sort of viewing our scene, so talking about cameras, and then rasterizing our triangle finally. Okay, so again, there's some stuff missing, texturing, lighting's missing. And a few other abstractions. So I think this could be a really cool final project if someone says, hey, after doing this OpenGL stuff, I want to implement some of it from scratch to really understand it. That would be a cool project. Okay, but at this point, again, it's time to introduce some hardware acceleration, right? We pay a lot of money for those graphics cards, so let's take advantage of them. And the reality is, even on our phones, we have graphics cards. They're integrated and maybe less powerful than the ones you have in your laptops and your desktop machines, but they are pretty powerful, and in reality, they're used for a reason because they really make the graphics better, more energy efficient, all of these things. And they support OpenGL. So just talking about hardware accelerated graphics a little bit here. Here's our graphics card. So far, again, we've done everything that's sort of CPU based. But if we think about, a game or a graphics application, because we're talking about real-time graphics in this course, we're really going through and keeping our CPUs quite busy, right? They have to look through each individual pixel, fill it in, draw a line, right? We sort of did all that computation. And, that alone is taking a lot of time. If you were going to see how busy or how much of your CPU you're utilizing in the task manager, for instance, our software renderers are keeping it very busy. And keep in mind, we need games to be running anywhere between the 30 and 60 frames per second range, or if you're in virtual reality, at least 90 frames per second. So it's really nice if, along with all the other things your CPU would have to do, such as the artificial intelligence, handling input, handling physics, all these other things, if you had a dedicated device to handle at least the rasterization part, that's really expensive. And that's really what the invention of the GPU was made for. Okay, we're going to find out the GPU can be used for a lot of things, but that's what it's designed for. So, how we get more performance on our machines is we try to implement different abstractions. So the GPU, for instance, acts as, we say, a coprocessor. So it's assisting or working with, that's sort of the prefix co here, coprocessor. Our CPUs, our other processor here, to do dedicated graphics tasks here, okay? And if we just look at the infrastructure here for the difference between a GPU and a CPU, our CPU, the thing that does the number crunching, has a bunch of these things called ALUs, which are arithmetic logic units. We'll just look over at the GPU here, and it has, many, many rows of these ALUs on it. So you can go ahead and see how many it has here compared to the CPU. The CPU has, some RAM. The GPU has a little bit of RAM, the cache, but the CPU has a lot more of these control units for handling things like branching, if-else conditions, etc., where the GPU just has like very little ones. So you can see that the architecture or overall design shows that, hey, this GPU is really for number crunching and doing math computation for the most part, okay? So the way that this works is the CPU is going to send data periodically to the GPU. So it's going to be here spinning and send some data to the GPU. And this is geometry data like our vertices and triangles that we want to fill in. And it's going to decide, to do, some matrix multiplications to transform things. And we saw how, involved those are. But the GPU can sort of crunch and process those. Okay, and the GPU is going to run through some pipeline here. So here's the pipeline that we've learned about. While meanwhile, the CPU, while the GPU is busy doing all that math, can handle other things like user input, loading files for the disk, any artificial intelligence algorithms that need to process, and so on. Okay. Then the GPU is going to at some point finish and say, hey, I'm done rendering the frame, and send it back to the CPU, which can then be displayed somewhere. Okay. So again, the GPU is accelerating or sort of taking care of in parallel that task of rendering the graphics, while the CPU can be free to do other stuff. So that's really this idea of the separation of concerns between the CPU and the GPU. Okay, so as time has gone on, though, we've decided that, hey, these graphics cards are really useful, so we're going to evolve our graphics pipeline. So really early GPUs or graphics cards, allowed us to have this sort of separation of tasks that we previously described. So again, our CPU being responsible for handling things like loading files with all the geometry and information, sort of like your PPM image loaders. We're just loading the information, searching for it on the disk, parsing it, and so on. But meanwhile, you could have had the GPU doing other sort of interesting tasks, the image processing things like lightening the image, darkening it, and so on, okay? So you can sort of see what's going on in the CPU in our graphics pipeline. It's from a graphics perspective, it's just generating the vertices, maybe from a file, or you're manually specifying them, processing them, and then the GPU does the rest of the stuff. It's going to say, hey, you have those 3 vertices that you sent in? Okay, that's a triangle. I'll build the line segments, I'll generate the fragments and fill them in, and display them out. Okay, and so again, our GPUs are quite good at this hardware acceleration thing. So over time, we said, hey, can we do this vertex processing? Can we also do that on the GPU? So this newer GPU here, the ATI Radeon 9700, which must have been around 2003 or 4 in that time frame, decided, hey, I can actually start doing some of this vertex processing and this other fragment processing, but you can actually program on this GPU now. So you don't have to send back and forth information as often, okay? So then a few years later, this thing sort of evolved our GPU and its capabilities into what's called general purpose GPU programming, GPGPU. That's a little bit of a mouthful, but that was the idea. And now it said we could write programs that execute on the GPU and have much more flexibility with how we're using each of those cores, those ALUs, but plus a little bit of logic on how we did things. Okay, so we're getting more cores and more power as time goes on, and more capabilities in our GPU. So now we're able to do more and more stuff, which is pretty cool. So we can sort of track this with OpenGL, which is the API we're going to be using. And you can see the pipeline here, OpenGL1. And the green boxes are the stages that you can do on the GPU. So here you have a couple things that can be done on the GPU. But then here your pipeline gets actually smaller, but you're handling more in each of these green boxes. Then we're getting more green boxes here for more things that we can do on the GPU, which is kind of cool. And in each of these green boxes, what we're really doing when I say we're adding capabilities is we're making them more programmable. So I can write programs that execute on the GPU. Okay. All right, so we're past all the sort of old OpenGL fixed pipeline stuff and doing programmable or GPU programming nowadays. Okay. Okay, so no more fixed pipeline because we're moving on to modern OpenGL. Okay. So as stated from day one, if you remember way back in our day one lecture, that we're going to be working with modern OpenGL. So again, OpenGL is a specification that individual vendors, folks like NVIDIA, Intel, AMD, Qualcomm, Apple, you, for instance, if you're building the great looking renderer, could implement in your hardware, if you built your own hardware. These companies make up a board and they sort of agree on what OpenGL is going to be and its future direction and what it's going to support, and that's the hardware that they sort of build to support that. Okay, so what we get from OpenGL or from these vendors, depending on what graphics card or processor you have, is a C API that can talk to your hardware. Okay, and build these sort of programs. Okay, so let's take a look at the modern OpenGL pipeline. So we have these functions available to us from this API, and we have circled in orange here for now these two boxes that we're going to focus on that allow us to program what the GPU is doing. Okay. The other thing to note about OpenGL is that it's a state machine. Okay, that means we basically, when we're using the API, it has this sort of large global state. We call this the OpenGL context, but it keeps track of all of the OpenGL things that you're going to do. How are you going to draw things? What version is your OpenGL? What functionality does it have? How many objects do you have in your graphics environment? How many vertices? All these sort of things. And this, again, controls how this, this pipeline that's shown on the right operates. Okay, so let's take some more views of the graphics pipeline. We're getting more familiar with steps 1 and 2 because that's what we've actually implemented, sort of taking in vertices and then rasterizing them. But when we're filling them in, we have this other step here that says, okay, not only do you fill in the triangles, right? Once you figure out which ones to fill in, that's really what the rasterizer is doing. But you can actually figure out, how do you color these? Do you color them based off of some sort of light source or some sort of material? And that's the idea here with the fragment processor. Okay, and then you eventually output that image to your display here. Okay, it's pretty rad looking monitor here, I guess. So that's another sort of nice view of the graphics pipeline. Okay. So with that said, though, let's get into the big ideas. These are really the two big ideas. They're in gold, so you know that they're important in this class. And I'm just going to tell you, right from the start what the big ideas are and what you're going to be doing in this course. And again, it might not make sense, but that's why we're going to practice, right? You're going to have labs where you can do some little exercises, and then the assignments where you do it from scratch. But the big idea is you're going to have some vertex data or whatever data you want, something about the geometry, and you're going to put that data into a buffer and send it to the GPU. Okay, so that means you're going to be sending vertex data that's going to exist on the GPU where all of these sort of number crunching takes place. Okay, you can do your logic on the CPU. That's, moving around, pressing buttons, handling user input, loading files. But in the meantime, the graphics operations happen on the GPU based off of that buffer of data that you've sent over. Okay, that's the first big idea. The second big idea is that on our GPU, we're going to be executing programs that we write. And these programs are called shaders. Okay, they're a little bit of a strange name. They're called shaders. You might think they have to do with coloring or filling in, and in part that's true, but there's many different kinds of shaders. But these programs are just programs that are going to execute using whatever the data is on the GPU. So they're executing on these buffers here and saying, what do we do with that data? Okay, so we're going to let those ideas sink in throughout the course, buffers and shaders. Okay, so buffers, again, a big idea. Number one, just to go a little bit more in depth on this is, just think of it as an array in C++. It's just a container that holds a bunch of data. And in OpenGL, we're going to use the API, and we have different ways that we can interact with those buffers, I guess. And there's different kinds. So there's something called a frame buffer, which is where we store pixel information. So we've been sort of lightly introduced to that idea. We've got buffer objects, which sort of store the geometry, vertex and index buffers or pixel data and so on. We're going to have texture buffers where we store information that we can draw on and so on. And that's what's passed between the CPU and GPU, these different types of buffer that contain specific types of data. And we access those pieces of data through a pointer. Okay, so now we sort of understand why pointers are useful, because they're going to give us addresses back to things that exist in memory on the CPU or things that exist in memory on the GPU. Okay, big idea number two with shaders is that they're just programs that execute on the GPU. OpenGL has sort of a C-like language for writing shaders called GLSL. And we're going to write specific shader programs depending on what part of the graphics pipeline we're working on. So vertex shader is going to control how the vertex data is processed in our graphics pipeline. Fragment shader is going to execute and control how fragments are drawn in our graphics pipeline. Okay. So again, and there's going to be many different types of shaders that we can use depending on what version of OpenGL we're using and how far we sort of get in the course for our capabilities. Okay. Okay, so just getting started though, for today, our goal is going to be just to achieve what we've done in our software render in roughly one day, but this time on the GPU. Okay, we're going to just render a triangle, put the geometry data in a special buffer called a vertex buffer object. And I'll go ahead and just abbreviate this because you're going to see it as VBO on occasion. Then we're also going to render that same triangle, but in a more efficient way in what's called an index buffer. In fact, in the second part of the lab, you'll render a rectangle. Okay, so at this point, if you need, we've been going on for a little bit. I know that's a storm of information, but go ahead and give yourself a little break if you need, and then we will resume. All right, so if you gave yourself a little break, let's go ahead and continue on and talk about what you're going to be doing for today's lab. Okay, so for part one, we're going to be rendering a shape. And, we need to sort of understand the code base we're working with. OpenGL's evolved quite a bit, so we just want to spend a little bit of time on things, so we have to really understand a little bit of SDL, which you've got a little bit of exposure to by design, the OpenGL graphics pipeline, again, which we've talked about, and then shaders. So, these sort of a couple different components here in this class, okay? So in the olden days in OpenGL, we used to just create our programs by just saying GL begin, and then we would specify the vertex positions here. So now we have a better approach though, because remember, one of the big ideas with OpenGL is this idea of buffers. We're just going to pack all this information into a buffer and then draw this triangle, okay? So let's do things in the modern way. So what we're going to do is, we want to store this information somewhere. So I'm going to create here an array, and here's a way to initialize an array here, a float of vector positions here, where x is the position of our first vector and y would be the next position of our next vertex. Excuse me. So this is our first vertex on this row, and then our second vertex has an x and a y here, and our third vertex an x and a y here. Okay, so we're going to send that information into a vertex buffer object. So a vertex buffer object is something in OpenGL that we can use to store and pack information into. Okay, again, when you hear the word buffer, just think about bytes. Okay, that's all we're really doing here. We're just storing a bunch of data somewhere. Okay, so in order to create our triangle, we need to put vertex information into some buffer, and then we tell OpenGL, hey, this is what we want to draw on the screen. It comes from this buffer, and then we sort of communicate with OpenGL that the information in this buffer is a bunch of positions of x and y. We might add color later, or texture, or normals, or whatever other information that we want. Okay. So how do we do this in OpenGL? Well, we have a handy function here called glgen_buffers. And we're going to see this pattern of code a lot. And you can see my comments from this, from our lab today, which you'll have. And we're going to generate, well, how many buffers? One. And where are you going to put them? Well, this is the sort of handle to the buffer. It's just going to be some integer here. Okay. So the way that OpenGL works is you just have a this sort of handle system where you say, hey, how many buffers do I want? One, and then your order sort of comes up here. So if you want, you can think about this as walking up to a restaurant, right? You're at Subway or something, the restaurant, and you say, how many subs do you want? One, and then they'll give you sort of a ticket, and that says, whatever your order number is here, and that's where all the information is going to be stored. I mean, maybe that's the way to think about it. Okay, so then whenever you have this handle, your order here, and whenever you want to use it, you bind to that buffer. You're sort of selecting and saying, hey, I want to use my buffer now. Okay, I'm going to do something with it. Then you specify what type of buffer this is with gl_array_buffer. Okay, so it's just an array of things. Now, okay, now that we've we're bound to our buffer here, we've binded to it. We need to actually talk about what the data is that we're going to send into that buffer. So this is a GL array buffer. And what are we going to put in there? Well, we're trying to draw a triangle which consists of 6 vertices. So 6 times however big a float is. And we'll use GL_float in OpenGL. That'll be about the same as, size of float for the data type. Where that data is coming from, the actual array here, vertex positions, and what we're going to do with it. Well, we're just going to sort of statically draw. We're not going to change how these things are drawn. Okay, so again, Y6 here, we have 6 floats representing 3 vertices, each with an X and a Y position. Okay. So again, just making sense of the data. Here's how our data is laid out here. And this makes sense to me if I lay it out here. But how is this different from below here, where I have the vertex positions here? Is this an X, Y, and Z? X, Y, and Z, 3 dimensions, or is it X, Y, X, Y, X, Y? Well, OpenGL doesn't know. We know because we laid it out in the source code this way, because we used white space efficiently, but OpenGL doesn't know. So we have to think about that in a way. Now we need to tell OpenGL, hey, this is how the data is laid out, okay? Is it 3 vertices with an X and Y, or 2 vertices with X, Y, and Z? Okay, so this is our next step. So we have this thing called GL vertex attrib pointer, which says, okay, we've got some piece of data here. It's some attribute. Okay, we're going to say attribute 0, because we count from 0, is going to be vertex information. Okay. So it depends, how much information we have here. If it's an X, Y, and Z, then the size is, 3 here. What the type of information is data normalized, and so on. Okay. So let me go to our actual lab here, lab number 5, and let's see what we did here. So lab number 5, in our first shape, in our source, in our lab. And oops, that's not in there. It's an STL graphics program. I believe I'm doing everything. GL attrib. Let's see. Let's see where we set this up. This will be a good. Okay. Attrib pointer. So if we're passing in an X, Y, and Z, well, our size is 3. So am I passing in an X, Y, and Z? Yes, I am. X, Y, and Z. Okay. So let me actually just get a capture of this screenshot, put it into the slides here, just so we can, just so you have a reference of what this refers to. Size is 3, and I'll draw a little arrow to it just so you can see. because it's a little bit confusing since I showed the example with 2 here. So now for your actual lab, we're using size is 3 there. Okay. Okay, so that's great. We have all of our data. So let me make sure I didn't go through this too fast. We have all of our data. We've put it in a buffer, and we've communicated with OpenGL that, hey, in our layout here, the first attribute that we're passing in is consisting of 3 things and X, Y, and Z. And now when we want to draw our triangle, we'll draw from 0 to 3. Why 0 to 3 here? Well, we have 3 vertices. So we're going to draw all 3 of them to make a triangle. So this needs to be set accordingly. Okay. Are we ready to draw our triangle yet? Well, almost. Okay, we have all of our data populated, right? We've populated the buffer, but we haven't communicated what our pipeline is. Okay, so let me just sort of add some notes here that, again, we're not quite ready because we've completed big idea number 1, which is just putting data into a buffer to ship to the GPU. And now we need to complete big idea number 2, which is to write a shader that communicates what to do with the data in our buffers for our graphics pipeline. Okay, so shaders, again, the little programs that execute on the GPU. So at this point, again, what is a shader? Well, it's just a tiny program that runs on your GPU. Okay, just like, we've been writing little tiny C++ programs that execute on our CPUs. These are programs that run on our GPUs. Okay. Now, why is this difference important? Well, optimization is one reason, and the other, because again, that idea of having a coprocessor that can execute while our CPU is doing something, but the other is that the GPU just needs to know what to do. We have to tell it, right? It doesn't have anything built into it. Okay, so again, as I mentioned, there's different types of shaders. We're going to focus on the first 2 in this class: vertex shaders and fragment shaders. Fragment shaders, depending on what API you're using, meaning if you go and use Direct3D or Metal or Vulkan, they might call them pixel shaders or something, but that's the idea. Okay, so what is a vertex shader? This first part of our pipeline that we have to program. Well, this is a program that runs once for every vertex that exists on the GPU. And it controls where a vertex final position is. That's its goal. So it's going to have a version number, what it's taking in. Well, we're taking in a bunch of, positions for our vertices. That's what our input is. And then, because that's the job of a vertex shader, take in a bunch of positions, your vertices, and then position them. Has nothing to do with shading or coloring or really, you can specify vertex colors if you want, but that's really all there is to it. Then the second part is, our fragment shader. We can think of them like pixels. Fragments technically a little bit different, but the fragment shader's job is to perform the rasterization and figure out, hey, what do we fill in? And eventually, how do we want to color things? Okay. So here's an example fragment shader that's going to figure out how do we color something? How do we color every fragment in our program? So we have, again, the version number, and then this time an out variable. We'll talk a little bit more about GLSL and doing some interesting things with it. But we want to figure out what's the output fragment color going to be. Okay, so for each fragment this is running on, and maybe I should go back and specify a few things with our vertex shader. So just to be clear, it runs once for every vertex that exists on the GPU. So I want to make that same sort of highlight on our vertex shader. A program that runs once for every fragment on our screen. Okay, so that's kind of cool when we think about it. What this program is doing. Oops, there we go. Just highlight it. So this program is going to run. If I've got a screen that's, well, let's do the calculation here. If my screen is 1,280 pixels by 800, something like that, this is running for each of our fragments, assuming it's completely filled, 1 million times basically. And it's doing, if we're doing 60 frames per second, So per second times 60. I mean, this program's running a lot of times, this little tiny program, if our screen's completely filled. So you can imagine why we need a GPU here and why it's so important to be able to do this and do it quickly. But what our fragment shader is doing is just something very simple, where it's going to, for every fragment, it's just going to output the color 1.0, 0.5, 0.0, and then the alpha is 1.0. So it's fully filled in. So it's going to just fill in every fragment in our program. Okay, that's the idea. Okay, now the other thing to keep in mind, and there's a little bit of a write-up on the lab to make use of this, is how do we use these shaders? Do we have a special IDE? Do I compile it with G++? These are the shaders provided in your lab here. So let me maybe make some notes here for clarity. So for today's lab, however, shaders can be loaded as external files or otherwise simply be loaded as strings in your programs. OpenGL, let's see how to say this. The OpenGL API has functions for compiling and linking your shaders. Okay, so let me make this a little bit smaller just so you can see everything on the screen. Sometimes I have to do these live edits. That's how these slides get long. But just to explain what's going on here, and this is probably worth drawing here for folks here, so just so you can see that, so we're going to have our CPU here. It's going to send some data over to the GPU. Okay, this is the buffer. So let me draw it like here. It's just a bunch of information, the buffers. And then we're also going to send over a GPU program, which is called a shader. But when we do that, we're also taking that shader source code, whatever it is, and we're compiling it down to a binary. So 10, 10, 10, 10, etc. So get the binary. So the shader source. So the program could just be a string, a file, whatever, and then that is put onto the GPU. Okay, so we're going to have this separate sort of stage where that's taking place. Just to sort of make that clear. This is going to become a little bit more clear throughout the semester, but again, today is about giving you sort of a higher level intuition here. Okay. Whoops, you might have missed part of the drawing here. Let me bring back my screen. Oops, I don't know if folks missed that drawing, so let me redraw it here. Sorry, technical difficulties. But just to reiterate it, because I think it's really important just to give you the high level intuition of, again, starting out with a CPU program that's running and running and running, and it's occasionally passing these buffers here. These are our geometry, vertex, positions. For now, that's what we're sending over to our GPU over here. But we're also sending these shader programs that look something like this. And these actually get compiled into binaries as well. So here is the little binary that I was writing. And then this executable gets stored in memory somewhere on the GPU. And it knows how to then take in this buffer information and crunch the numbers, get some result that we eventually send back and display on the CPU. So again, just a high-level diagram of what's going on here. And this will make more sense as we actually do it and get to practice it. But again, just the high-level view of what's going on there. Okay, so this slide sort of goes with it, but you're going to find in your support code this idea of compiling shaders. Okay, so this is done when the program runs. You can do it beforehand, but we're going to always do it while the program's running. So when our program starts, it's going to create this program here. That's our shader here. Compile the vertex shader, compile the fragment shader, attach them together into this program here, link them, check for bugs, and then we're done. Okay, so this is essentially creating our graphics pipeline here. Okay, you can sort of think of this as like a pound include here, but we're saying, hey, the vertex stage, it's handled by the thing called, well, whenever we compile the vertex shader with the vertex shader source. Hey, the fragment shader, that thing's done whenever we do the fragment shader thing with the fragment shader source code. Okay, we put those together, link them, and then make sure the program is valid as stated. So here's the idea. We can have multiple different shaders, multiple different sort of pipelines. Again, that's what makes this powerful. And then we just select between whatever pipeline we want to use, depending on how we want to draw a particular object or part of our scene. Okay, so that's the idea there. Okay, so let me take a moment there just to note that later on, you're going to see, common errors like getting a blank screen, like when this part of this recording disappeared, or if it disappeared or not. I can't remember. But the idea is, if you get an empty screen here, often it's because you didn't build the graphics pipeline, right? You didn't go through this step and create and link a program that could be used to draw your graphics scene. Okay. Maybe you're missing part of the vertex shader or part of the fragment shader, or you will get compile messages, error messages in the vertex or the fragment shader. So I'll just go ahead and make that note here. Note, you may get compile errors in either the vertex or fragment shader. Check your console to make sure. Okay, so those are some common errors. Another common error. So it's another place to look for errors in your program, I guess. But it will warn you. It'll do a pretty good job. And the programs are usually relatively simple, so the debugging is not too bad. Okay. All right, so you're going to encounter a lot of new commands today. And I want to introduce this site called docs.gl. I'll just go ahead to it now, docs.gl. And you might have some of these commands like gl compile shader, and you're like, hey, what does it do? For the most part, most of us are using OpenGL3. You might be using 4, so you just click on the whatever the version is, and that's it. So I'll go ahead and leave this here. This is a really helpful resource. So whoever made this resource, thank you to them. Okay, so today's lab, as mentioned, is 2 parts. It's a 2-parter. So you're going to notice there's a little bit more support code here. And you're going to be working in the STL Graphics Program CPP, okay, for your tasks. You'll notice there's a little bit of an object-oriented structure provided. I might modify this throughout the semester, depending on feedback or to make things easier on folks or whatever. But just so you can get an idea of what's going on, okay? The main goal is going to be to just render a triangle and make it a different color. Okay, so that's your goals for part 1 are going to be to render specifically a blue triangle, change the background color of the scene, so you can look for GL clear color. That'll be a little hint, see what that does. And then change the size of the triangle, okay? All right, but we're not quite done. At this point, there is a part 2 for this lab in which you'll be working with something known as an index buffer, okay? So today's goal, or the second part of the lab rather, is to draw more complicated shapes, okay? How we're gonna do that. So in this case, we're gonna learn how to draw a rectangle, hooray, our first, rectangle, and do so in a more efficient manner, okay? So an index buffer is gonna be our trick, okay? So you're going to start with what's, a triangle, which is great. That's what you're doing in part 1, where you stored, the vertex and information in a vertex buffer object. So, think about that. And then you thought about, what's the fragment color that I'm outputting. But what we really want to do, and figure out is how can we draw, more complicated shapes. So here's our sort of OpenGL coordinate system, right? And we sort of have these normalized coordinates from 1 to -1 in the X and Y dimension. And, we want to draw more complicated shapes. So something that's important is the winding order. So as I told you before, let me bring myself on the screen here for just a moment, is if you take, we're in a right-handed system, so take your sort of right hand and make the sort of coordinate system with your hand here. And the direction that your fingers curl when your thumb's pointing you is what's called the winding order. Okay, so you can see the little illustration below, but this tells you when you have a triangle, right, you can imagine it having only one side in the graphics world, and you want to know where the front is and assume the back side is sort of hollow, which is sort of weird for a triangle, but there's sort of a front face and a back face. We want the front face to face towards us. So that means you have to specify the vertices in the order of the winding order. So in this case, it's counterclockwise. Okay, so I'm starting here, then going here, then going here. And that's how I'll have a triangle that's visible to me or know which side is the front. Okay. Okay, so I know if I plot these vertices here, here, and then here, that's a counterclockwise order. Here, here, and here. Okay, it doesn't matter what you do, but you do have to be consistent. And there's different ways to set it, okay? So this is how we need to specify our vertices. That's the first thing to note. Okay, so if I want to draw two triangles, I just use more vertices, right? I'm going to specify 3 for the first triangle, 3 for the other one. But my goal is to draw a rectangle which only has 4 vertices. So I should be able to reuse some of them, okay? If I look through this data, there's redundant data here. I have 0 twice, okay? So that's wasteful. And as we generate bigger and bigger 3D object files, this could become more and more wasteful because we'll really be duplicating lots of information. Okay, so here's another, duplicated vertex and so on, right? You have 2 duplicates, 2 pairs. So again, let's just try to visualize what we've done here. So every 3 floats are a vertex, the x, y, and z. Here's the sort of first vertex. I'll just index 0. The next one, the next one, the next one, the next one, and so on. And then I can draw this rectangle here. It's just a black rectangle here. It's shaded in. So here's index 0, 1, 2. That's one triangle. And here's index 3, 4, and 5. The next triangles. Okay. But again, I really only need 4 indices here. Okay. So the trick is in OpenGL is we have our second buffer type, which is called an index buffer, okay? Or they'll call it GL element array buffer. So elements, the indices, elements in your array, if you want to remember that way, that we also can send along to our GPU specifying the indices that are in our vertex buffer, okay? So we have 2 buffers, one with vertices, vertex buffer, and vertex related information, and one with elements, the element array buffer, okay, or index buffer. Okay, so here's the old way with a GL array buffer. And what you're going to do is generate a new buffer for these indices. Okay, so reminder on binding buffers here, create a second buffer. You use GL gen buffer to do that. And then this time we're not using array buffer, but this new type, GL element array buffer, okay, that we're going to put indices into. Okay. So now when it becomes time to draw, you're just going to draw 3 triangles. You're still going to do that, or at least 3 indices, okay, that you want to draw, and what that sort of range is, I guess, of indices that you have available. But you need to specify, how many total indices you have. And so if you're just drawing the triangle 3, if you're drawing a rectangle, well, how many indices do you have? So kind of think about that. And the indices, again, well, I needed to specify here in this example, 1, 2, 3, 1, 2, 3. Okay, so I'll let you think about that. It's not how many total unique ones you have, but how many do you need? Okay, so you can actually try some different examples there. Okay, so the second part of the lab is going to be figuring out how to use that buffer and how to, there'll be some little to-do marks for how to properly draw a rectangle. And then based off of the what the user presses, a button, it'll draw either part of that triangle or the full rectangle. Okay, it'll draw either the first few indices or all of the indices. Okay, so again, and you'll have docs.gl if you need help, as always. Okay, so that's the second part of your lab 2. Okay, and then of course you have an in-class activity with that. So let me bring myself back into the screen here for just a moment. And tell you, I think this is the real exciting part of the class that we're diving into OpenGL. So go ahead, get started, make sure you knock out part 1 first, look at the to-dos, and then start working on part 2. I can also recommend, so in the resources, for today, there's a bunch of readings, and I'll highlight this one here, the sort of hello triangle, and make sure that you're doing, some of the readings here. It's really going to make your life easier if you both see the slides and then read through another perspective. The Learn OpenGL tutorials, again, this is what we're following for the course. If you're ever looking for help, we're roughly following, this order or this content here. So this is your first place. It'll explain what a shader is, how to compile, what an index buffer is if you sort of look at hello triangle and then go to shaders and so on. And then we'll get into the transformation stuff as well. So do look at those resources. They're super helpful. And, this is going to be fun to see what it took us a few days to get to. And then in OpenGL, we can draw a triangle in sort of a cool way. So with that said, folks, have fun with this one, and the labs will be in your repositories by the time you have seen this video.